especially the organizers for organizing this nice school and for giving me the opportunity to lecture about scattering amplitude and also report on some work done with my collaborator that I will mention in future lecture. So the title that was, I think, proposed by the organizer was scattering amplitude and integrability. So it was a bit ambitious and maybe too broad because I mean, integrability has a lot to do with scattering amplitude. We learn it thanks to lecture by Dory, and I'm not sure I could explain better than needed this nice relationship between asymmetrics in general and integrability. And what I really want to talk about is a particular case of scattering amplitude, which is scattering amplitude in this rather exceptional theory, which is planar and equal to 4 superiorities. So I assume you are a bit familiar with this theory because I think it will pop up also in a lecture by Claudia and by Pedro and maybe by other people. So I don't know if I should introduce it, but if I had to introduce it at the level which is needed for this lecture, the only thing that you probably need to know is that it is a sypersymmetric version of your theory, this I assume you know, in 4 dimensions, and with the maximal possible amount of supersymmetry. So we put all the matter, if you want, fermions and scalar, which is needed to form a perfect and equal to 4 multiplex. And with this large amount of supersymmetry, we expect to be able to do a lot more than what people can do in pure Young-Mills. Of course, pure Young-Mills is way more physical and relevant to our world than n equal to 4 super Young-Mills, but studying n equal to 4 super Young-Mills is interesting because it is believed to be the simplest possible interacting 4-dimensional gauge theories. And we believe that if we manage to solve it, we will learn something about more generic gauge theories, especially at coupling and also perhaps in the strongly coupled regime of the theory, where a lot of nice things happen in this particular theory. So the word planar refers to a particular limit of this theory that we are considering. So the theory comes with a gauge root that I can choose to be UN, and being the number of colors, and also with the Young-Mills coupling that give me the strength of the interaction among the gluons. And the limit that we are considering is this limit where this coupling is very small, but at the same time the number of colors is very large, such that the effective coupling at a certain level, which happens to be the top coupling, the product of G of Mills by N, is arbitrary. Okay? So the theory is still non-trivial, despite the fact that it's a weak coupling G on this limit, precisely because we are taking simultaneously a large number of colors. So maybe, hopefully, it will become a bit clearer later why we lack this limit. And I wanted to say, so maybe someone will need more motivation for studying an equal to 4 super Young-Mills, because as you will see, this theory actually defines a conformal field theory, which means that there is no in this theory there is no spectral problem to solve at the level of the Hamiltonian. We know exactly what is the spectrum of the theory at any value of the coupling. It's just a random collection of massless gluons and superparsecs. There is no more than that. They cannot bind. There is no confinement. There is no running of the coupling. There is nothing funny happening. So in a sense, from this point of view, the theory is excessively simple. There is another spectral problem which is hidden, which comes about when you start thinking that it's actually a conformal field theory, and this is something that we've learned during the talk by Osborne, which is that we need to solve for the spectrum of scaling dimension of this theory. And we will hear a lot about this problem during the talk by Claudia, and also I guess during the talk by Pedro, that will also consider the construction of 3-point function. additional piece of information that you need to characterize your conformality theory. Okay? So the motivation was that it's probably solvable. Okay? And there is this sentence by Wiseman, by Seibert, I think I heard it during one of his lectures, which is that if there is something that you believe you can solve, then you should solve it. So maybe we don't need motivation. Just that it seems that we can solve this theory within our limit, and it will be a pity not to try. And beside it, as I said earlier, it might tell us something about more generic gauge theories. And there is a bonus, which is that if we manage to solve this theory, we are also secretly learning about another important class of systems that we care about, which is gravitational theory. So you probably heard about this Nordita conjecture, or in modern term, ADS-CFT correspondence. And this theory is one instance of this ADS-CFT correspondence, the claim being that n equal to 4 super-Young is dual, meaning equivalent to a theory of superstring in a anti-de Sitter space, in a 5-dimensional anti-de Sitter space. So if we manage to solve this theory, we are secretly, implicitly solving a non-triggered interacting gravitational theory, and this is very exciting. So here the challenge is to try to do as well as what people did for string theory in flat space. So you know that string theory in flat space is very well understood through the study of two-dimensional CFT and so on. We can do a lot of things. We can compute the spectrum. We can talk about the scattering of strings. We can compute it order by order in the genus expansion up to relatively high order. Here we would like to be able to do the same in this string theory in this curved background, which is a much more difficult background. And what we have learned through the last maybe 15 years or so is that the right technique, it seems, is perhaps not to think in terms of two-dimensional CFT, so to study the worldsheet theory in the conformal gauge, but to choose a particular gauge where the problem become equivalent to solving an integrable Basso two-dimensional field theory. So integrability pop up in this context as a substitute to the usual conformal field theory techniques, and the goal is to try to develop these formalisms as far as we can in order to be able to compute anything we might be interested to compute in this particular string set. So this is for the big picture. And then you could say, okay, but why scattering amplitude in particular? And well, people have solved the spectral problem. Some people are solving the three-point function problem. So we need to find another problem to solve if we want to exist. And so we focused on this case of scattering amplitude because if you open a textbook, it is yet another of these textbook observables that you are instructed to construct at some point in your career. Okay, so this is the motivation. So roughly, the plan of my talk will be so the first lecture should be rather basics, but I will try to introduce a bit of formalisms that people refer to as modern formalisms for studying scattering amplitude, in particular in massless field theories. So it's not necessarily specific. What I'm going to say is not specific. It's not necessarily specific to n equal to 4. It might also apply to QED and so on, perturbatively, or other theories, massless theories. But of course, I will try also to use as much as I can of supersymmetry, which is available in this theory. We have plenty of them. As I said at the beginning, it's a maximally supersymmetric version of your waves. To put to zero to whatever I can put to zero. Okay, what should vanish by supersymmetry, I don't want to consider. I want to know from the very beginning that there is nothing to consider there, and then try to move a little bit off these zeros and find what is the simplest possible amplitude. So So there is a zoo of amplitude that you might guess. We have plenty of particles we can play with and scatter. We can play with the number of legs, we can play with the flavor of the particles, we can play with the number of loops. So it's a huge enterprise to compute this scattering amplitude. So the starting point is to try to find what is possibly the simplest of all. Try to focus on this particular case and go as far as we can. So in the second step, that will be we will try to enter a bit more into the subject of this lecture and find some sort of hidden duality or yet another bonus symmetry, if you want, of this theory, to reformulate our problem in a new language, which will allow us to import some techniques of conformal field theory for studying scattering amplitude. These techniques will be the formulation of the operator product expansion that Osborne talked about for local operator, but to adapt it to the particular case that will be relevant here, which will be the case of Wilson blocks, so some non-local observables that are conjectured or believed, to some extent proved, to be equivalent to scattering amplitudes. And then I will talk about something more recent, which is the work done with my collaborator to use integrability techniques for computing this Wilson loop. So that will be a class of Wilson loops that we cannot study using localization. It will be different from the cases that Nadav will be explaining to us pretty soon. But here again, we will find some help in this new tool, if you want, this recent tool, which is integrability. And maybe if we have time, I don't know, we will see how far we can go along this line and what we can learn. So getting back to the first lecture, so here is a set of references for the first lecture. So as I said, this is what I'm going to say today. It's mostly background. It applies to many theories. And everything that I'm going to say is somewhat taken from these references, which I use for writing this lecture. And it's much better said in these references. So if you are really interested in all the details and even the big picture, I strongly recommend you to have a look at one of these references, to pick something, look at the picture. This one in particular is pretty recent, so it covers a lot of recent developments that I will not be able to talk about. But it's hundreds of pages, so I guess none of you will read it by tomorrow. But again, if you find something suspicious during my lecture, you interrupt me, we try to clean it up, and if we cannot, then we need to go to this references and see what these experts are saying in this subject. Okay. So let's get started. So what we want to do is just open a textbook, look at some picture, and see that we need to draw some sort of diagram like this. Okay. Well, this means, roughly speaking, sum over all possible Feynman diagrams, which are allowed in your theory. Put some external states, so I will choose them for simplicity to be gluon. Okay, so G will be not gluon in this lecture and will disappear completely in the next lecture. It will become something else. So, but here it should be okay. So of course I have other stuff in this theory, but I want to talk in particular about gluon because a lot of what I'm going to say is treatable, okay, which is already a difficult problem to solve. And because it's treatable, whatever you do at tree level in this supersymmetric theory is also directly applicable to non-supersymmetric version. Because at tree level, gluon scattering, you cannot produce anything exotic in the middle, you cannot produce scalars or fermions. So all the diagrams are the same as in QCD, they come with the same weight, and so the answer in the end should be exactly the same. Okay? So it's a bit more of motivation for looking at this particular scattering event, which is that we are learning something about geometry. So they carry a lot of information with them because, as you know, these gluons, of course, they are massive. They have some momenta. So let's call it 1, 2, 3, and so on, up to n. So they carry some momenta. They are all masses. Okay, we are considering, of course, on-shell scattering amplitude. And they also carry some polarization vector. one for each of them, which are also subject to some conditions that I will write shortly, so I don't want to write them now. And they also have some color. Okay, so they have some index A that runs from 1 to n squared, which is, again, related to the rank of the gauge station, which I choose to be U1 for simplicity. But of course, U1 is just U1 plus times SUN. U1 is the photon decoupled, and so on. But it's actually useful to carry the photon around. It brings some extra information sometimes. Okay? So this is a problem, and it is complicated particularly because of all this decoration and so on. We need to, and the fact that in practice, writing all the Feynman diagrams and performing all the Feynman algebra is a real pain. Whether try to do it, know that it's really, it does not look like a very efficient way of computing, and often it becomes hopeless. So people looked at this problem a long time ago, and they progressively understood how to organize things, such as to make the problem a little bit simpler. And I will try to bring you through this step. Okay. So the first step is to do some color ordering. By this we mean that we will decompose the amplitude of a particular basis in the color space. Okay, anyway. So what happens is that we have our blue one, and of course they are naturally attached to some generator of the UN algebra. Okay, that we choose to be in the fundamental representation. So it's a matrix which carries some fundamental and anti-fundamental index. So it's an n by n matrix. This runs from 1 to n. This runs from 1 to n. So pictorially, I will draw something like this. There is A. Then I just open it up so that I have this famous double line notation that you might have seen elsewhere. And this, again, it satisfies some algebra. In this algebra is this T, TA, TB, TB, TA is equal. I'm using perhaps some funny normalization. I'm just trying to follow the normalization, so it's a bit irrelevant. These FABC are totally antisymmetric. Okay? And we can also write the very same thing by contracting and using the fact that we're using some normalization, which is as a trace of the product with delta AB. Okay, so this we can multiply on both sides, take the trace, and read out FABC in terms of some trace of a triple product of this matrix. Okay, this is very simple algebra, and I don't want you to remember this, but the only thing that we're going to need, maybe all of this is very elementary. If you think I'm going too slow and you know all of this, please just tell me, and I will try to accelerate. So we can rewrite it like this. So it's antisymmetric, so it's an object that takes three gluon. Here there is a loop of fundamental stuff. It's not something dynamical, it's just some color contraction. And because it's antisymmetric, we want to tackle also the inverse ordering. So this is our representation of this Feynman rule at the level of the color. I might also mention now, or maybe there is also a piece. There is also a kinematical factor. This vertex has this color structure, which comes also multiplied by. We write it here, but it's very not important. Just to refresh your memory. If I have three incoming momenta, so these are my momenta. These are just Lorentz indices, Q, rho. Then there is a piece that takes into account the kinematics, the dynamics as well, from the way, which is this P minus Q mu, okay, plus permutation. Actually, it has to be. Okay. Let's write it down. So you don't need to write this down. Okay, it's in the textbook. You open it, you find, you go to the end of the book. Typically, they put this at the end of the book, and you read the Feynman rules. Maybe the normalization will be different, but otherwise, it's. So the full vertex is totally symmetric, okay, under permutation, but you can decompose it into an antisymmetric piece in color space times an antisymmetric piece in the real space. And why are we doing this? Because now imagine that we compute some amplitude. Let's take the simplest thing that we could do, like some tree diagram like this. Okay, and we'll number this guy for just number who is who. Now we can use our rule to see what kind of picture we are getting. You see it's very simple. So now I can replace this. I can put my circle here with some circulation. I can do the same here with the same circulation. Okay, then I can fuse these two lines together. Okay, and I will get just one big loop in the middle with my stuff attached around. And because I have, you see, this minus here, the fact that this is antisymmetric, I know also to take into account all the possible, so in this diagram I need to take into account permutation here, and double permutation, okay? And sum over all these possibilities. And the main message is that after recognizing that this is nothing else in terms of color, from the color point of view, then the trace of each T that I am putting along this A1, TA2, TA3, TA4. Now making this straightforward observation, what I get is that my amplitude, AN, with N blue on side, at 3 levels. So this is the full thing. Let's put full here. Can be written as, maybe I want to, from the very beginning, to 3 parts on GL mills. So you know the rule, each vertex consumes GL mills, and so on. So if you count how many vertices you have, and so on, you get this power for n dual scattering. And then you have this sum over what? Over all possible permutation. That will denote like this, say, divided by cyclic permutation of some sub-amplitude, AN, here I'm still at 3 level, which now only depend on the P and epsilon. So the color is gone. Okay? This is the sequence. The main message is that the color is gone. Times the trace of T A sigma 1 dot T A sigma n. Okay? This amplitude, this sub-amplitude is called partial amplitude, color order amplitude, many names. And they have these properties that they only have cyclic symmetry. Okay? So you see they multiply something which is cyclic invariant. So you can move things like this or like that, but you cannot do any other permutation. The full object, of course, describes the scattering of bosons, so it's totally invariant under any sort of permutation. And this is realized because we take something which is cyclic invariant and we sum over all the possible orbit of the permutation group. Okay? So the full object is invariant, but each one of these guys now has this kind of topology. Okay? So this is the first simplification. We don't have to worry about the color anymore. That was for 3 level, and at 3 level, any amplitude can be decomposed over this basis, which is called single trace. So here, you have indeed a single trace of product. Okay. This is not true if we go beyond 3 level. So just for illustration, if you open perhaps one of these reviews, the first one, I guess, you will see that if you consider the 4 particle scattering, at the next order, you will get G on mix to the 4 now. Okay. So for 4, you get 2 at leading order, 4 at the next order. And if gets multiplied by the number of colors times something which is the very same type of thing as before, except that now it's a loop correction to what was standard here, times the very same trace, But you also start adding something which comes with the same power of G on this, but with no dependence on N, which is a sum again about some sort of subgroup, or sort of quotient of the permutation group. But it's a kind of new object. It's still a loop right here. But now it multiplies a double trace structure. Okay? This is what you can see at one loop. You have a new amplitude. So of course what you want to do is that you want to collect this A3 and this guy to it, define a finite coupling partial amplitude associated to single trace. But then you will have also to do the same for all the substructures that you can produce when you increase the power. Okay, it's not that you can produce indefinitely many of them. For a finite number of gluons, you will have a finite basis of possibilities. But at some point they will pop up. In our case, the only amplitude we're interested in is this class of amplitude that receives this kind of correction. Okay? Because we see that they are suppressed by this particular combination of the coupling times the number of colors that we want to call lambda, okay, and the Taft coupling, and that we want to keep fixed while we take this G on is going to 0. So by doing this, we select out this particular class of diagram, which has this simple topology here, single trace topology. Okay, single it out from the rest. And the idea behind it goes back to Taft, and it has to do with the fact that if I start putting now more line here, and I do all my color construction, I will start to see this structure, but there will be this particular diagram which has this particular structure that they will look like if they were drawn on a planar surface. Okay, these are called planar diagrams. And eventually we will have a lot of this loop as we inside this hole as we increase the number of loops. And we could imagine that if we put a lot of them together, we are actually filling up the disk here, so that at the end we are describing a kind of stringy process where we attach some vertex operator to some planar surface. Okay? So this is the string theory description that Taft has seen emerging out of the color structure of Feynman diagram in gauge theories, and which was perhaps the first hint at a sort of duality in a sense between gauge theories and string theory in general. So it becomes especially clear in this limit where we take the Taft coupling to be whatever we want, which means that we have a particular tension for the string, and we do not permit for the formation of handle and so on, or some sort of change of topology, which has to do with this string genus expansion, which is much harder to deal with, and which we prefer not to consider prior we understand the planarity. Okay. So, of course, in this theory, we have already some idea about what is going to happen. We know that there is indeed some sort of dual description, but it is not living in the space we started from. It is not living in 4 dimensions. It is living in this dual AES-phi space. And at some point, we will have to get there and try to see what string theory in this space is telling us about scattering amplitude. How string theory is seeing this object that we are painfully trying to compute by some Feynman diagrams. And what it is telling us about it and so on. And this is from the next lecture. So any question about this? So perhaps it's a bit too slow. I guess some of you might have seen a lot of this already during the study or by reading papers. So there are some funny things also that you can play with if you're interested. So I mentioned the fact that we could work with UN or with SUN, it's relevant. if we work with UA, then we have this photon, and we could imagine taking one of these guys here to be a photon. Okay? Then we know in advance that this photon should not scatter with the gluon. So the amplitude should just disappear. Okay? And the T associated to a photon will be just the identity. So then we can collect all the terms. You see that if one of these T is the identity, then it's totally irrelevant the ordering. I can put the photon on the first place because it will commute with everything. I can collect all the terms of the same type and just claim that they should be zero because I know that this amplitude is zero. Okay? This is the photon decoupling identity. And that gives me a set of relationships that link this three amplitudes upon some particular permutation of their argument. Okay? So these amplitudes, they are not all independent, there are some relationship. I don't know the complete catalog of relationship, but this playing with this photon is one way of getting such information. Okay. So what is the next step? The next step is that try to do something for the kinematics. So we have all these indices and so on, this polarization vector. It's painful to carry them around all the time. So we would like to find formalisms which is as friendly as possible also with the other kind of excitation or particle that we have in this theory, and in particular spinor. So we have this fermion, they belong to the smallest possible representation of the Lorentz group. Okay? This left and right representation of SL2C. And because it's a supersymmetric theory, and because we know that this smallest representation in principle can be used to build a bigger one, we would like to know whether we can use the same kind of variables or spinors for everyone. And this happens to be especially simple to set up in the case of massless theory. This is what is called the spinor helicity formalisms. And it applies to massless theory in general, not necessarily to this, especially in this supersymmetric theory. So what we do is that we introduce these Dirac matrices in this bind representation. So it boils down to some off-diagonal matrix with the sigma matrixing, which are just the identity and the Pauli matrix. Okay, so this we should know. And we also introduce the sigma bar, which is the same thing, but with some minus in front of the sigmas. Okay? And then what we do with it is that we represent our vector, P mu, as a matrix. Okay. So it's a matrix, it has left and right index. Okay. A and A dot. Take value 1 or 2. Okay. And if you want, just use the expression for the sigmas. It's pretty straightforward, and you get this expression. Okay? So this way, RP is more naturally embedded in the natural space of our two-dimensional spinor that we need for handling the gating. So what is nice about it is that if we want to compute, for instance, the p-square, so the p-square is just the determinant of this matrix. So I will also use this notation. Sorry. This. And sorry, I think I want to say this notation. So this is a matrix, and the determinant of this matrix is equal to p squared and is 0 because of particular masses.
Sorry, simple question.
Yes.
And probably p's in the matrix are also upright.
P0, P3, so let me see, for instance. Okay, sorry. I'm not reading my note carefully yet. Yes, so there is a lot of minuses floating around as soon as you change something. So, okay, that should be more or less correct. Okay, actually, I'm not sure that I collected several things from several reviews. I didn't check the consistency of their convention and notation, so there might be some mismatch. Okay? But in principle, it's just convention issue. Okay? The main idea should be correct. So what this is telling us is that this matrix has a rank which is at most 1. Okay? And assuming that our P is not 0, okay, which will be the case where P is just nothing, we can write it as a projector. Okay? What we can do is that we can represent this matrix A dot as the left-handed spinor times a right-handed spinor. Okay? So the fact that the excitation is massless gives us the opportunity of describing our momentum, or equivalently this matrix, as a product of two spinors, okay? Which are smallest object to deal with, and so on. Is it clear? Yeah. That's the main point. I don't know who found this first, but it's a nice point, and this is the main point. Then it is also convenient to introduce yet another notation. All of this is just rewriting and so on, but there is some advantage in doing it. So, so first I can introduce some epsilon tensor. Let me define it here. Epsilon 1, 2 is equal to epsilon 2, 1 is equal to 1. Okay, and otherwise antisymmetric, totally antisymmetric. This way I can raise and lower the indices whenever it's needed. So for instance, I can define, now there is a sign, no, there is no sign. I can define a lambda, okay, with the A at the top as being epsilon AB times lambda B. Okay, it's as simple as this. And I can do the same with dotted object. So by the way, you see that if P is real, then this matrix is Hermitian, and which means that this lambda and lambda theta has to be complex conjugate of one another. Okay, so if we assume some reality condition in a particular signature, because all of this depends on the signature of the space and so on, then we get some reality condition on this lambda. So sometimes people they talk about scattering amplitude in a different signature and so on, or they complexify. And then lambda and lambda tilde becomes independent from one another. So you just remove this reality condition. So now that I have all my ingredients, I set up some notation, which I don't know if it is, hopefully it is going to be more intuitive for you than it is for me. So I will write that my lambda A, I will just rewrite it like in sort of a bracket stuff. Bracket notation. Okay, so when it is left and down, it is of this type. When it is left and up, it is like this. Okay, and when it is dotted, and up, it is like that. Okay. So the goal being to having some sort of Dirac-like notation and progressively get rid of all possible indices, and but still conserve a bit of the logic. And the logic comes from the fact that now we will start defining some inner product. So you see that using this epsilon tensor, which is an invariant tensor under SF2C, I can now form some quantity which are invariant under the Lorentz group. Okay. So, by the way, in this notation, the very same thing here can be written as mistake because I was using different notation before, and now I get confused between this angle and square bracket. But okay, it's not very important. There is this object that you can also relocate. Okay? So now the inner product, they are naturally defined by taking, if you take two spinor, what you want to do, for instance, is that you want to define something like this. Okay? Where you solve over A. Of course, it's the same as doing epsilon AB, lambda A, UB, which you will also rewrite like the order. Okay? So it's just a product.
When you write P there, PA, P dot, should it be lambda inside brackets or?
Yes, sorry. So, yeah, I guess if you stick to this, it should be a lambda. But in practice, people use, as soon as you have this mapping, you want to put something, you need to put something here that is meaningful for you. It could be whatever you want, but it has to remind you that it is the momentum that you start with. So sometimes people put P, or sometimes people put lambda of P, and so there is a lot of possibilities. So we have this product, and of course we can do the very same thing with.
Excuse me. Yes. No, those should be done because you're using angular brackets.
Yes, good. Yeah, thank you. You mean this? With this? Yeah. Okay, yeah, I have alternating nodes, so I don't know. Anyway, it's not very important. Well, it becomes important when you do explicit computation, and so here you do the same, and you define this other product, which is lambda mu. Okay. Great. So we have two kinds of product, and they are some sort of square root of Mandelstam invariant. So the way you see this is that you, if you take, for instance, this lambda mu, now I'm going to use this word. Let's see if you like this new thing. Now if I take some spinor I and another spinor j and form this kind of product, this is equal to this product. So what does it mean? It means you take P, okay, it is a massless momentum, so you can write it like this. So you get your lambda and lambda tilde, which are associated to this pi, okay? And then you do the same for pj, and then you form this product. You have two such a product, but when you multiply them together, you realize that this is nothing else than the Mandelstam invariant. Okay? So this is Sij. So what this product are? Just some square root of this Mandelstam invariant. The name? The name of what? Mandelstam? Mandelstam, sorry. So this is the same invariant as Patrick Dury was talking about. And these are some sort of square root of it that we can define for this massless master. So, well, I leave it to you to prove this. It's not very difficult. I could help you, but I think I don't have time. So, yes. So we have this. Now we are not yet done because we need also to define our epsilon tensor. Sorry, not our epsilon tensor, our vector polarization in terms of this new ingredient. If we want to get something which is more uniform, we get to define this. And the prescription is the following. So you can have two polarization, plus or minus. So epsilon plus of associated to some particle with momentum p is given by square root of 2 qp times p q. And for epsilon minus is a complex conjugate, and if I write it in the same what kind of property does it satisfy? We have this property that p epsilon plus minus of p is equal to 0. They are also null. And they are orthogonal in the sense that they are subject to this normalization, assuming this, always assuming this signature of space-time. And beside it, they also satisfy the very same relation here, but with Q. And now you should ask me what is Q, because okay, P we know what it is. We start with some gluon, and this gluon has momentum P. Okay, now we just attach to it some epsilon, which by construction is orthogonal to it, and so on. Okay, but this Q, so this Q, it's a residual gauge degrees of freedom. Okay, so it's a non-shell gauge degree of freedom that we can introduce for. I mean, we can define this epsilon in many different ways, and this is reflected by this Q. Okay, and if you want to check it, you could compute, for instance, you could compute the difference between epsilon plus, which is built out of some Q tilde, and an epsilon plus, which is built out of some Q. Okay? And what you will find is that you can rewrite it in this form. So this is an exercise. So do you see what this means? So this you should not pay too much attention to it. It's some factor, call it alpha if you want. What is important is this structure here, which is nothing else than P. If you think in terms of vector space, it's nothing else than P. So this is just telling you that changing Q, changing this reference spinor, as a name that it has, changing this reference spinor is equivalent to shifting epsilon by some P. And indeed, if P is massless, then shifting epsilon by P does not change anything about this normalization. So this is a residual on-shell gauge symmetry. So physical quantity, like scattering amplitude in particular, on-shell scattering amplitude should be totally independent on whatever value of Q you choose. So if you decide to choose some Q, if I decide to choose another Q, at the end of the day, if we compute something which is gauge invariant, it should not depend on it. If you take a random diagram, okay, just one diagram in a series of diagrams, then it might very well depend on Q. But the sum of all Feynman diagrams, assuming it is describing some physical observer, should be independent of this Q. So what this is telling you in practice is that you can play around with this Q to try to cancel as many diagrams as you can. When you compute a diagram, you have this freedom of choosing this Q, and you can choose the Q you want for any particle. You can choose the Q1 for the first one, the Q2 for the second, and so on. The only thing that you should make sure is to use the same Q for all the diagrams. You cannot change Q for a different set of gauge invariant diagrams. But in practice, if you want to choose Q, and if for some choice some amplitude happens to be just simpler, even vanish, then you are really instructed to do it. And this is an art, and this is quite an interesting art actually, which allows you to immediately draw some consequences about certain scattering amplitude. This is what much time do I have?
I guess 9 minutes.
9? Oh. Okay, so I guess we... don't get as far as I want to. So, what are these amplitudes that we can easily simplify by playing this game? So one of them is let's just consider 4 gluon scattering. Okay. So we consider something which has just 4 gluon attached. Okay, 1, 2, 3, 4, and we consider that here is just 3 diagrams. So now we need to pick the helicity. So it can be plus or minus and so on. So what is your guess for what is the simplest possible amplitude, assuming that helicity are measuring with respect to all incoming gluons? Okay, so you know that helicity depends on whether you're flowing upward or downward. Okay. So what would be your guess for the simplest possible amplitude? Sorry? Ah, yeah, you're smart. But let's imagine I want to scatter gluons. Okay, I don't have much time, but I'm sure you will find out. So it's plus, 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 plus. Okay? So why is it so? So first, imagine we could draw the diagram, we could compute all the contraction and so on, and we could realize that we are wasting our time. Because there is something that you can see, which is that for generate-free amplitude with n gluons, you will have, by using the rules here, and by, so first of all, you start with n epsilon. Okay? You have n epsilon because you have 1 epsilon for each length. Okay? So if you have n gluon, you have n epsilon. And then the question that you want to know is how many of this epsilon gets contracted with one another. Okay? So you need to know how many possible momenta you can get in the denominator of this amplitude. So you know that you will get some in the numerator. You know that you will get some denominator which corresponds to all the Mandelstam invariant that you have in the middle and so on. But you will get also something in the numerator coming from this rule. See this momenta and so on. And the point is that you can at most have n-2 momenta, which is the maximal number of 3-point vertices that you can have for a 3-level amplitude. Okay, so it's a bit of topology of diagram. You can see that you can have at most n-2 momenta. Which means what? Which means that we can take n-2 of these momenta and contract them with some epsilon. But we will always have 2 epsilon which cannot be paired with some momenta. So they got to be paired together. Okay, so it can be I and j. I don't know. Here it could be 1 and 2, or 1 and 4, or 1 and 3, and so on. And now you see the point is that here we are scattering only pluses. And you can play with this expression here. You can put some P1, Q1, and some P2, Q2 for epsilon 1 plus and epsilon 2 plus. You can contrast them, and you will see that this is proportional to contain P1, P2, Q1, Q2. Okay? Which is telling you that if you choose the Q to be the same, because this product is antisymmetric, you should get 0. So just by choosing, just from the knowledge that you are computing the 3 amplitude and from the fact that you know how many momenta you can have at most in your numerator, you know that you will necessarily have a term of this type. It has to be there. Okay? And so by choosing the Q, for instance, to be the same for everybody, for sure all the contraction will go to 0. So this diagram is 0. Okay? So just by choosing the Q, in this case you can kill all the diagram one after the other. Okay? It's just impossible to avoid this conclusion. So this is sorry.
Can you be sure that you
Yeah, so Q is my reference spinner. So it's something which I can choose the way I want. So of course I could choose Q to be as something which is vanishing in the denominator. That would be really insane. Or I can choose I can put Q to whatever value I want at the very end. So it's completely up to me. Okay. So Q is not related to P in any way. It's freedom you have to choose. Okay. So this is for sure the simplest possible amplitude. So somehow we answer the question, but this is not the answer I wanted to get today. But this is quite amazing to see that this is 0 for such a simple reason. And actually, it's not the only amplitude that is 0. If you take one guy to be minus, if you take also one guy to be minus, this is also 0. So now you need to be a bit more careful because still we will always find some pairing of this type. But now it is not necessarily 2 pluses. So of course we could choose 2, 4, and we could choose 2, 3, and 4 to have the same Q, and then we will kill all these terms. But now we need to pay attention to the fact that epsilon 1 in a color order diagram can also talk to 2 and 4. We can also have something which is of the type epsilon minus 1 dot epsilon 4 plus. Okay? So this kind of quantity now, they are in this kind of configuration, what we have is that we have the momenta of this guy. Yes. We have that the momenta of this guy talk to the Q of the other guy. P4, Q1. Okay? So if we choose all of this guy to be the same, and proportional to P1, then we can also kill this kind of term. Okay? Whether it is 4 or 2 does not matter, because we can choose the Q to be the same in both cases. So now we see that if I choose Q4 to be P1, I am killing also this term. Okay? So for this kind of amplitude also, just by looking carefully at what kind of structure I can have, I realize that by playing with this Q, I can kill this amplitude.
Strictly speaking, this only throw away from the primary. If P4 is equal to P1,
okay, okay. You mean in the collinear limit, this will be like a free particle vertex. If I take the collinear limit of 2 of this guy together. So what I'm saying does not apply if you are thinking about free particle scattering, which is really special. But I'm not sure about your collinear limit.
No, I mean that you can choose P4 to be P1, but only when P1 is not equal to P4.
I'm choosing Q4 to be P1.
Right, but this means that Q4 should not be proportional to P1, to P4.
Ah, okay, sorry. Okay, you are referring to this.
Yes.
Okay, okay, yes, you're right. Yeah, so, yeah, collinear limit is probably a bit tricky. I'm not sure about. Okay, I'm not sure. Sorry, thank you. So I think I'm out of time. So I was planning to go a bit further, but anyway, okay, I will give you some appetizer. I will try to finish all of this at the beginning of the next lecture. So, what is the conclusion? Is that we were looking for simplest possible amplitude that we could try to compute to higher loop possible. And so far we didn't find anything. So of course there is a question, the important question of whether what we've just observed, that I am generalizing here to n part and gluon. It's a question of whether this remains true or not at higher loop. Okay, so it's definitely not true in QCD. So everything we say at 3 level is true in QCD, again for the very same reason as before. There is you cannot feel the extra matter which is present in the supermultiplet, so it's the same computation in both theory. But in QCD, when you go to higher loop, when you see the difference between whether they are gauging or not, and this is important. So the claim is that these two equations follow from what is called SUSY word identity, which in other words is just a consequence of supersymmetry. Actually, you only need one supercharge. So here we have 4 supercharges, so you can imagine that we might find a lot more relationship, and indeed one can find a lot more relationship. Not vanishing like relationship, but relation between different amplitudes which are not necessarily 0 and will be independent in a random theory, but are linked together in an equal to 4 superamplitude. Okay, so 3 is very special. Sorry. So first, 3 does not exist, strictly speaking, or only exists for collinear configuration if you have massless particle. Or it also exists if you allow yourself to work with complexifying momenta, and this is a vertex that plays a very important role in some approach for computing scattering amplitude in an equal to 4. But here, you see, I started with 4, and I want to compute. So I consider that 3 is trivial. That's my prejudice. Okay. So the first amplitude, which is non-zero, is called maximally ABCT violating so-called MHV amplitude. And it is, when you think in terms of scattering of gluon, it is of this type. Okay? So every 1 plus except 2. And this guy is non-zero. Okay? And not only it is non-zero, but it is nice. At 3 level, there was a conjecture which has been proved later on by Park and Taylor. For 4 particles, we were supposed to compute it for 4 particles, so maybe we will do it next time, but I'm not sure. It's a nice exercise. It was supposed to be a kind of trying to push the same logic that led us to the cancellation of this guy for 4 particles, trying to push it a bit further for this MHV amplitude. See that in this case we cannot get all the epsilon contraction to vanish, but we can make things. We can make a choice we just pick up 1 diagram. So instead of considering, so here there are not that many diagrams. If you count how many diagrams you have only 3, but still 3 diagrams, it's a lot of contraction. And we can choose our Qs again in such a way that only 1 diagram contributes. And then it's relatively easy to guess what can happen in the numerator and in the denominator, to carry out the algebra and to find this formula. So this one is much more general because it applies for any number of gluon, and it takes this form. Okay? So I guess that will be the last formula for today. This is at 3 level. Next time we will talk a bit about what is happening. And is, I mean, for many reasons an important formula because when Park and Taylor conjecture it, I don't know if people believe it immediately or not, because if you really think from the point of view of Feynman diagrams, it's really a lot of Feynman diagrams that just resum in this simple expression. And some people get amazed by the simplicity, and they thought that, okay, it cannot be that the answer is that simple and there is no way of deriving this simple result in a better way than by using just resolving by brute force Feynman diagrams. So the simplicity of this result triggered a lot of development in the subject and a lot of re-understanding or re-analysis of scattering amplitude, which has led in particular to BCFW recurrence relation, if you heard about it, a lot of things. Okay, a lot of things that happened in this field, as far as I understand, was produced somehow by this simple formula, which is amazingly simple. And all of this development, you see that all of this thing we went through today was just to set up the alphabet to be able to write this simple answer. Okay. So next time we will. So the conclusion is that we found our simplest possible amplitude, which is not zero for the moment. Okay, maybe later if it vanish, we will see. So this amplitude is not zero. It is especially simple. And the question, the immediate question is, can we go beyond it? Can we now start adding loops? How much difficult it is becoming, and so on? And can we find some way of using integrability for pushing ahead this endeavor? Thank you very much, and sorry for being on.
Questions, comments? Maybe some time for a quick question. So I have a very trivial question.
Yes.
So when people usually say that all plus amplitudes and all except one plus amplitudes are similar, implicitly they are fixing all the reference.
Okay. So it proves that I was too ambitious. I was not very clear. So the amplitude here, this amplitude is gauge invariant quantity. So this Q is a residual gauge freedom that you have. Which means that whatever quantity you compute which is gauge invariant should be independent of Q. So you can, if you want, compute the very same amplitude that we computed, started with random Q. Okay, you can choose them randomly. Then you won't keep any diagrams from the very beginning. You will have to take all the diagrams into account. More particularly, they are not that many anyway. And you will find that they surprisingly cancel out. So each diagram individually is not gauge invariant. So whether it is zero or not, it's a question of gauge. You can choose a gauge in which a particular diagram is zero. The sum of all the diagram is gauge invariant. This should have a definite answer, whichever way, whichever choice of Q you make. So when people say that all pluses or all but one pluses amplitude are zero, they either mean that it is zero at tree level in QCD, or it is zero at any level in supersymmetric theory. Because this is the consequence of supersymmetry. But it has nothing to do with gauge. It's totally free of any gauge choice. We are just trying to use, so this is something which I think is much more well explained in this review by Gans. This is the art of choosing, adapting your gauge such as to simplify your computation. It's a bit like when you try to do some computation even for scaling dimension. Sometimes it helps a lot on a specific problem to choose the right gauge, because you will just reduce the number of diagrams. The answer that you get at the end, if you are computing something which is gauge invariant, should not depend on this choice, but you can just make your life easier.
Sure, but since it afflicts the matrix, also I guess that you can choose to choose once and for all. You can't make a different choice for each one.
No, you can make a choice of Q. If you take a quantity and you know that this quantity is gauge invariant, you can make any choice of Q for this full object. If you can think of I hope I'm not telling you something wrong, but when you do the computation as a loop order, you have some loop diagram, and this set of loop diagram is on its own, after summing them together, it's something which is gauging up. So if you want to change the Q while going from 3 to 1 loop, you can in principle, because you can see it as a new gauging quantity that you are trying to compute. So I don't think you commit to use the same Q once and for all. It's as long as you are staying, within a set of diagrams which is gauging. So I think. I guess.
So you should, there is no.
Do you have a simple formula also when you put more minus?
That's a very good question. I was supposed also to explain this. So one of the goals of this lecture was to give you some sense of what are the most complicated or the simplest amplitude. You see, just to you don't want to attack the problem, pick randomly an amplitude, and realize later on, once you did already a lot of computation, that it was the most possible amplitude you could have chosen. So you want to understand, organize them. This is where supersymmetry helps a lot. And what you understand when you go through supersymmetry in particular is that amplitude becomes more and more complicated in terms of structure and so on, as you increase what is called the MHV degree, which in terms of gluon amount to flipping more of these classes. Okay? So of course at some point, if you have finitely many gluon, if you flip too many pluses, you get something which is parity conjugate to something that could be 0. So this MHV degree depends on how far you can go in this direction, depends on how many gluons you have from the beginning. So for instance, for 4-point amplitude, there is only MHV. You cannot flip more because then you get something which is 0. Okay?
But if you have 8 gluons, can you have 4 minus and 4 plus? So
for instance, if you have already 6, you can have 3 minus and 3 plus. And this is an MHV amplitude, okay, which is more complicated than the MHV one, in the sense that this is also something that you see more easily. At least I see more easily personally through supersymmetry, because you essentially when you increase this MHV degree, you increase the degree of a certain polynomial in some Grassmann parameter that take into account all the possible how many degrees of freedom that you might want to switch off to go through your multiplet, your entire multiplet. And this degree grows, which means that you have more and more amplitude to compute. So MHV is unique. You tell me compute MHV amplitude, I know exactly what I have to do. You tell me compute an MHV amplitude, if I think in terms of components, I would have to compute several components, and so it's a bigger object. In the sense, I think we can say that it is more complicated object. So, but for a given component, it might forget. It's more complicated, more structured.
So we should end this lecture once more.